In this video, we're going to talk about critical points, local maxima, and local minima. Let's start with the first derivative test. If f prime of x goes from positive to 0 to negative, then there will be a local maximum at the point where f prime of x equals 0, just like in that diagram there. Similarly, if f prime of x goes from positive to undefined to negative, and if f of x is defined at the point where f prime of x is undefined, then there's a local maximum at the point where f prime of x is undefined. We'll talk about that later in this course. Similarly, if f prime of x goes from negative to 0 to positive, then there will be a local minimum at the point where f prime of x is equal to 0, right there. And again, similarly, we'll talk about it later in the course, if f prime of x goes from negative to undefined to positive, and if f of x is defined at the point where f prime of x is undefined, then there will be a local minimum at the point where f prime of x is undefined. Okay. Now, we'll see that sometimes a curve can have a tangent line that actually crosses through it. Sometimes we have a situation where f prime of x goes from positive to 0 to positive. Look at this curve. Positive to 0 to positive. In that case, there's neither a maximum nor a minimum. And similarly, f prime of x can go from negative to 0 to negative, and then in that case, there's neither a maximum nor a minimum at the point where f prime of x is 0. An example of a curve like this is y equals x cubed, and an example of a curve like this is y equals negative x cubed. Okay, now let's talk about critical points and critical numbers. The points at which f of x is defined and f prime of x is equal to 0 or f prime of x is undefined are called critical points. So again, f of x is defined, but f prime of x is either 0 or undefined. Those are called critical points. And the values of x at which the first derivative is either 0 or undefined, those are called critical numbers. So critical points, derivative is 0 or undefined. Critical numbers, that's the x value of the critical points. So let's take a look at this question. For the function y equals x to the 4 minus 8x cubed plus 18x squared, we want to determine all the critical points. And then we want to determine whether each of those values of x gives a local maximum, a local minimum, or neither. So, suppose we start with y equals x to the 4 minus 8x cubed plus 18x squared. Well, that would mean that y prime is equal to 4x cubed minus 24x squared plus 36. We can common factor 4x, and we're left with x squared minus 6x plus 9. In other words, 4x times x minus 3 quantity squared. Well, the first derivative is never undefined, but the first derivative does equal 0 where x is 0 or x is 3. Okay, good enough. What we're going to do is interval testing on an interval where x is 0 or x is 3. Letting x be a number less than 0 gives me a negative factor here. Now, x minus 3 quantity squared will be a negative quantity squared, which will be positive. So I'll have a negative times a positive if x is less than 0, meaning I'll have a negative first derivative. In between 0 and 3, this factor will be positive. This factor will be negative, but I'm squaring it, thereby making it positive, so I'll have a positive first derivative. And finally, a number greater than 3, all factors are positive, so the first derivative will be positive. So this is what the number line will look like. Now, we'll say that we've got critical numbers at x equals 0 and x equals 3. Now, the critical number at x equals 0 represents a local minimum. The reason it represents a local minimum at x equals 0 is our first derivative is negative and then it's positive. So that's a local minimum. And at x equals 3, there's neither a local minimum nor a local maximum, because that's a situation where we had a positive derivative and then a 0 slope and then a positive derivative again. And that actually is one of these situations here that we talked about earlier. Positive, 0, positive. So that would be neither a maximum nor a minimum at x equals 3. X equals 3, neither a local maximum nor a local minimum. Well, let's get the y values at x equals 0 and x equals 3. At x equals 0, plugging in a 0 for y, we get 0, so the point's 0, 0. And at x equals 3, plugging in an x value of 3 in for x, we get y equals 27, and the point is 3, 27. So therefore, the critical points are 0, 0, where there's a local minimum, and 3, 27, where there's neither a minimum nor a maximum. Here's another example. Determine whether the function y equals x cubed has a maximum or a minimum at, or neither, at c, f of c, where f prime of c is 0. Okay, well, if f of x is x cubed, then f prime of x is 3x squared. F prime of x equals 0, that would mean that x is 0. Well, at x is 0, y would be 0 cubed, which is also 0. So the point where f prime of c equals 0 is the origin, 0, 0. So let's take a look at our first derivative. Our first derivative is 3x squared. Well, when x is less than 0, I've got 3 times a negative quantity squared. That's positive. When x is greater than 0, I've got 3 times a positive quantity squared. That's positive. So I've got a positive slope leading to a 0 slope leading to a positive slope. As we saw a moment ago, there's neither a maximum nor a minimum at a point like that. Okay, our next question here. Determine the critical numbers for the function y equals the square root of x squared minus 4x plus 8, and determine whether each of those critical numbers represents a local max, a local min, or neither. So here's our solution. Y is equal to, instead of putting it in square root form, I'll put it in exponential form, quantity to the 1/2. I'm going to use the chain rule to find the derivative. 1/2 x squared minus 4x plus 8 to the negative 1/2 times the derivative inside, which is 2x minus 4. So that means y prime will be 2x minus 4 over 2 times the square root of x squared minus 4x plus 8. Factoring the numerator, I get 2 times x minus 2 over 2 times the square root of x squared minus 4x plus 8. Dividing top and bottom by 2, I get this expression right here. So there's my first derivative. Now, if y prime equals 0, if I put a 0 here and multiply both sides by this square root, I get 0 equaling x minus 2, or in other words, x equals 2. If I want y, if y prime is 0, x is 2. That's a critical number. But what if y prime is undefined? That also produces critical numbers. Well, if y prime is undefined, that would imply that this denominator equals 0. So that would determine that that would mean that x squared minus 4x plus 8 was equal to 0. All right, so y prime is undefined implies that. Well, if x squared minus 4x plus 8 equals 0, then using the quadratic formula, we see x would be equal to 4 plus or minus the square root of negative 16 over 2. That means y prime's never undefined, so the only critical number possible is x equals 2. Now, please note that x squared minus 4x plus 8 can never equal 0. We just showed that. It can't equal 0. So that means it's either always positive or always negative. Plug in any number you want for x, you'll see that it's positive. So therefore, x squared minus 4x plus 8 is always positive, so the square root of it will always be positive. So here we go. We've got our derivative, which we said at the bottom of the last page was x minus 2 over square root of x squared minus 4x plus 8. We've got that right here. We've just established our denominator is always positive. So I look at numbers to the left of 2, which is our only critical number. To the left of 2, y prime would be a negative quantity over a positive quantity, which is negative. To the right of 2, y prime would be a positive quantity over a positive, which is positive. So we've got the point at x equaling 2 being a local minimum. We're decreasing, and then we have a slope of 0, and then we're increasing. So the point where x equals 2 is a minimum point. Now, at x equals 2, y is going to equal the square root of 2 squared minus 4 times 2 plus 8, which is root 4, which is 2. So, at x equals 2, y equals 2, so the point 2, 2 is a minimum point. For our next question, we're going to determine critical numbers for the function y equals x plus 3 to the exponent 1/3. And then we're going to determine whether each of those critical numbers represents a max or a min or neither. Well, and as you now know, to get a critical number, we need to find the first derivative. The first derivative of x plus 3 quantity to the 1/3 is 1/3 x plus 3 quantity to the negative 2/3 times the derivative of x plus 3, which is 1. Simplifying this, we get 1 over 3 times x plus 3 to the exponent 2/3. And this is 1 over 3 times x plus 3 to the 1/3 quantity squared. So when you have a fractional exponent like that, put it in lowest form and then put 1 as your numerator and then put the actual numerator outside. Now, what we can see is that there's no value of x that'll make 1 over 3 times x plus 3 to the 1/3 quantity squared equals 0. Because if you put a 0 here and multiply both sides by that denominator, 0 would equal 1. So we can't have a possible situation where the first derivative is 0. But it is possible if x equals negative 3 for the first derivative to be undefined. So at x equals negative 3, the denominator equals 0. Therefore, at x equals negative 3, y prime is undefined. X equals negative 3 is our only critical number. So we have y prime equaling 1 over 3 times x plus 3 to the 1/3 quantity squared. If I let x be a number to the left of negative 3, the cubed root, that number plus 3 will be negative. The cubed root of that will be negative. But when we square that, it'll be positive. So I'll actually have a positive first derivative. If I let x be a number greater than negative 3, x plus 3 will be positive, the cubed root of that will be positive, squaring it will be positive, and 1 over 3 times that positive will be positive. So my first derivative will always be positive, except at x equals negative 3, where the first derivative is undefined. So at x equals negative 3, there's neither a maximum nor a minimum. Now, what does the y-coordinate equal at x equals negative 3? Well, the y-coordinate will be x plus 3 to the 1/3, which will end up equaling 0. So the only critical point is negative 3, 0, and that point is neither a maximum nor a minimum. Another question asks us to determine the critical numbers. Instead of x plus 3 to the 1/3, let's do x plus 3 to the 2/3, and then determine whether each of those critical numbers represents a max or a min or neither. Okay, so let's do our first derivative. We bring that 2/3 in front, and we have x plus 3 quantity to the negative 1/3, and then we multiply by the derivative of what's inside that bracket, which is 1. So we've got 2 over 3 times x plus 3 to the 1/3. Now at x equals negative 3, the denominator will be 0. Okay, at x equals negative 3, that factor will equal 0, and the third root of that of 0 is 0. So at x equals negative 3, y prime is undefined. By the same logic as in the last question, y prime can't equal 0. If you put a 0 here and multiplied both sides by the denominator, you'd get 0 equals 2, which can't happen. So the only critical number is x equals negative 3. Now, we have y prime equaling 2 over 3 times x plus 3 to the 1/3. Our only critical number is x equals negative 3. To the left of negative 3, I've got a negative quantity here. If I let x be a number less than negative 3, x plus 3 is negative. The cubed root of that is negative. 2 over 3 times that is negative. If I let x be a number greater than negative 3, then x plus 3 is positive. The cubed root of that will be positive, and 2 over 3 times that will be positive. So that means that at x equals negative 3, I've got a minimum value, because I'm going from negative to undefined to positive, but the curve itself is defined there, and so it's actually a minimum. So let's find out what the y-coordinate is. At x equals negative 3, y ends up equaling negative 3 plus 3 to the exponent 1/3, which is 0. So therefore, the y value when x is negative 3 is 0, so the point is negative 3, 0. It's the only critical point, and it's a minimum, as we showed here. In this question, we're going to determine the values of a, b, and c such that f of x equals ax squared plus bx plus c has a local maximum and passes through 8, negative 12. And that local maximum is actually at 5, 6. Okay, a little unfortunate there. I forgot to put it in. A little bit sloppy, but hopefully you can see that. It's got a local maximum at the point 5, 6. Okay, and it passes through 8, negative 12. Well, a local maximum at 5, 6 implies that f prime at 5 is 0. Okay, now I don't have to run into an undefined situation because I have a smooth polynomial curve. So as you remember from your advanced functions class, a smooth polynomial curve doesn't have any, it's smooth all the way through. We're not going to have difficulty coming up with a tangent line, so we don't have to worry about the undefined situation. So if we have a local maximum at 5, 6, that means f prime at 5 is 0. Well, if f of x is ax squared plus bx plus c, then f prime of x is 2ax plus b. Let's bring the 2 down, plus b. Okay, so if f prime at 5 is 0, then that means 2a times 5 plus b is equal to 0. Well, that means that 0 would be 10a plus b, which means b would be negative 10a. So we're going to remember that as equation 1, b equals negative 10a. Now, since the curve goes through 5, 6, and 8, negative 12, that means f of 5 is 6 and f of 8 is negative 12, just using normal function notation. Well, f at 5 is a times 5 squared plus b times 5 plus c, so 6 ends up equaling 25a plus 5b plus c, and that's equation 2. We know it goes through the point 8, negative 12, so f of 8 is equal to negative 12. I plug an 8 in for x, and I get negative 12 equaling 64a plus 8b plus c. That is equation 3. Now, we're going to take this equation 1, well, it said b equals negative 10a, and we're going to plug it into number 2. So doing that, we get 6 equals 25a plus 5 times negative 10a plus c. Remember, b is negative 10a. And when we simplify that, we get c is equal to 25a plus 6. We'll call that equation 4. We'll take this equation 1, b is negative 10a, and we'll plug it into equation 3. That would mean that 64a plus 8 times negative 10a plus c is equal to negative 12, which would simplify to c equaling 16a minus 12. So I see that c is 25a plus 6, and also c is 16a minus 12. Well, that means that 25a plus 6 must equal 16a minus 12. So like it says there, putting it together, we get 25a plus 6 equaling 16a minus 12, which means 9a is equal to negative 18, which means a is equal to negative 2. Well, b is equal to negative 10a, as we've said more than once, so b would be negative 10 times negative 2, which is 20. And then we can go back to equation 2 or 3. We could have plugged it into either of these, but we now know the value for a and the value for b, so we can figure out the value for c pretty easily. 25a plus 5b plus c equals 0, letting a be negative 2 and b be 20, ends up with, making c be negative 44. So we get a therefore statement of a equaling negative 2, b equaling 20, and c equaling negative 44. Now finally, we're going to do a question where we're given the curve of y equals f of x, and we have to determine the curve of y, we have to determine what the curve y equals f prime of x would look like. So what we're going to do is we're going to try to determine what the slopes are of various points on this curve. Well, looking at this right there, I can say that at that x value, the first derivative is 0. They're asking me to graph a curve of y equaling the first derivative. So at this x value, let's say it's negative 2. At that x value, the first derivative is 0. So that means at that x value, my y coordinate needs to equal that first derivative of 0. Now, over here at this x-coordinate, let's say this x-coordinate is 3. At that x-coordinate, my first derivative is equal to 0. Well, I'm asked to graph a curve where y is equal to that first derivative value. So my curve needs to have a y-coordinate of 0. Okay? Now, in between these 2 points, my first derivative is negative. Well, I'm asked to graph a curve where y is equal to those first derivative values. So I'm going to draw a curve that has negative y values. Now, to the left of this value, I see I've got positive slopes. So if I've got positive slopes, I've got positive first derivatives. Well, if y is supposed to be equal to those first derivative values, then to the left of this x-coordinate, I need to have positive y values when I graph y equals f prime of x. And similarly, to the right of this point, let's say this x-coordinate is 3. To the right of that point, I've got positive first derivative values. So I need to be graphing a curve that has positive y values. So my curve will look like this. Now let's ask ourselves, does that make sense? I would say yes, because if you look at the original curve I gave you, that is apparently a cubic curve. Well, I asked you to draw a sketch of the first derivative. Well, it looks to me like we draw a parabola. That makes sense because a parabola is degree 2, and the first derivative of a degree 3 curve will be a degree 2 function.